So the next lesson we're going to talk about is something called the Equidistant Theorem. So let's first go over a little bit of vocab. So it says the distance between two objects is the length of the shortest path joining them. A line segment is the shortest path between 2 points. And if 2 points are the same distance from a third point, say x, then x is considered to be equidistant from P and Q. So the perpendicular bisector of a segment, which we touched on in the last section, is the line that bisects and is perpendicular to the segment. So you're taking both of those vocabulary words and you're basically just combining it. All right, so let's go over these new theorems here. So, equidistant theorem. So it says if 2 points are each equidistant from the endpoints of a segment, then the 2 points determine the perpendicular bisector of that segment. So this is saying if PA and PB were congruent, and AQ and BQ were congruent, okay? So if you look, if we were to cut it on PQ, it's a mirror image on both sides. If you folded your paper, like a reflection, think of it like that. So if that is the situation that you have, then that blue line is the perpendicular bisector of AB, which means it makes right angles and it splits that segment in half. So again, it needs to be a mirror image. AB is not the perpendicular bisector to PQ, because if you folded it on AB, you would not get a mirror image according to those congruent marks. So PQ is the one we're working with. So basically what that would allow us is if we knew these two congruent statements right here, just based off that, you can jump right to saying that PQ is perpendicular to AB. So that would be the proof we had done last with section 4.3. It became a 14-line proof. It actually could be a 2-line proof. So these theorems drastically cut some of the proofs that you're going to do down. But again, the nice part is if you forget these, you always have that other way as a backup. And if that makes more sense to you, then certainly do that, because this is definitely not an easier concept to remember with this. All right, so we have the equidistant theorem, so it does have a name to it. And then we have the converse to the equidistant theorem, which basically means we're just flipping it. So instead of giving two sets of congruent expressions, we now know that something is a perpendicular bisector. So it says if a point on the perpendicular bisector of a segment, then we know that it is equidistant from the endpoints of that segment. So if we're saying PQ is the perpendicular bisector, then any point that falls on PQ, and in this case it's P or Q, is then the same distance away. So P is the same distance, if I use a different color here, is the same distance from A, and P is the same distance from B. Q is the same distance from A, and it's the same distance from B. If I had put, say, a point, let's say Z here, and I made segments, since Z falls on the perpendicular bisector, you'd be able to say that AZ and BZ were congruent. And I could keep adding points on that perpendicular bisector, and the same idea would be true. It would still be congruent with that. All right, so let me show you. I'm going to actually write these out because I don't have them on here. All right, let me switch my color here. All right, so we are going to do example 1. So I'm going to given angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. And we're going to prove that AE is the perpendicular bisector to BD. So this is not in the notes, so definitely add this in. 1, 3, E. I'm just going to set up my 2 columns. All right, so we know that angle 1 and angle 2 are congruent. we know that angle 3 and angle 4 are congruent. And we want to prove that AE is the perpendicular bisector of BD. So I'm just going to highlight this a little bit, this one right here. Okay? So thinking back to old stuff, if we focus just on the triangle above, we see that ABD, triangle ABD, is an isosceles triangle. Well, if angle 1 and angle 2 are congruent, then I can go to the sides opposite, which says across from angle 1 is AD, is congruent to across from angle 2 is AB. And they're congruent by the converse isosceles triangle theorem. The same goes for the bottom triangle, and it's the same reason, so I'm just going to include it in the same line. So I can say CD is congruent to CB. So this is congruent to this, and this is congruent to this. So I have now just created a diagram that has two sets of points, C and A, that are equidistant from two of the endpoints, B and D. Therefore, I can go right to my proof statement, which says AE is the perpendicular bisector of BD, and it's the equidistant theorem. Equidistant theorem. All right, let's try another one here. Example 2. Given triangle ABC is isosceles, where AB is congruent to AC, so that's given. If it wasn't given, you'd have to state that. E is the midpoint of BC, and we're trying to prove that AE is perpendicular to BC. A, B, E, and C. All right, so I got that and I got that. Now, if we're trying to show that AE is perpendicular, I would either need to show that two different sets of segments are congruent to use either one of our new theorems to get there. All right, so we've used the first part of the given, but we know E is the midpoint of BC. Well, if E is the midpoint, then I know that BE is congruent to CE. So BE is congruent to CE by definition of midpoint. Now, that just got me my two segments. So I can say that AE is the perpendicular bisector of BC using the equidistant theorem. And then given that that is not my proof statement, I have to add one more line that just specifies on the perpendicular aspect of it. And I'm going to write definition perpendicular. So you can see how much shorter these proofs get when you do these types of problems. All right, I'm going to do one more. I'm just going to erase the first one here. Actually, let's see if I can keep all this set up because I need it. Example number 3. All right, so one more. Example 3. All right, so we're given that AB is congruent to AD and BC is congruent to DC. And we want to prove that BE is congruent to ED. And we have this figure again. So we have A, B, C, D, and E. All right, so I'm just marking up what we have. So right off the bat, if we sort of look at example 2 below, I have that same picture in the upper half of what I have there, which means that just based on those two sets of congruent marks, I know that AC is the perpendicular bisector of BD. And that is the equidistant theorem. So I've already got that. But now think, if AC is the perpendicular bisector of BD, then anything that falls on AC would also be the same. So E is on AC. Therefore, since E is on AC, I can actually use both of those new theorems in one. So then I